Hey everyone, today I want to talk about automata theory, and in particular I want to talk about deterministic finite automata. Now, the end goal of this video is going to be to formally define DFAs, but in order to do that we're going to have to do a bit of legwork to get there, so just stick with me through the video and we'll eventually get to that point. But I guess the first question to answer is, what exactly is a deterministic finite automaton? Well, essentially, it's a specific type of finite state machine. So we're first going to have to introduce the topic of finite state machines in order to get into DFAs. So I think the best way to introduce finite state machines is to use the analogy of a car. So we're essentially going to build a finite state machine modeled after a car. So I want you to first consider what possible states a car can be in. And I think the easiest construction of this is that a car can either be stopped or it can be moving. Those are the two states that the car can be in. So in order to reflect this in our finite state machine, I'm going to use some circles to represent those states. So our first state is going to be the stopped state, and our second state will be the moving state. So these are our two potential states that our car can be in. It can either be stopped or it can be moving. So how might we want to transition between these states? Well, there are certain actions we can take, right? If we hit the gas pedal when we're stopped, we will transition to the moving state. And if we hit the brake on the moving state, we're going to transition to the stop state. So in order to represent this, we're going to use arrows. These represent transitions between the states. And I'm going to label this one gas because when we hit the gas pedal on the stop state, we will transition to the moving state. So this label here is essentially the condition that needs to be met to move from this state to this state. Okay, and then as I said earlier, we're going to transition from the moving state to the stop state when we hit the brake. So again, this label is the condition that needs to be met to take this transition. Okay, so at this point, we've kind of got a general picture of a finite state machine. We know that it's got a finite set of states. We've got a moving state and a stop state, and it's got some transitions between those states. We've got this brake transition and this gas transition. So in order to make this a little bit more analogous to DFAs down the line, I'm going to go ahead and add in a few more transitions. So you'll notice that we've only got one transition on the stop state and one transition on the moving state. But notice that we have two potential actions. We can hit the brake and we can hit the gas. So we don't really know what happens when we hit the brake on the stop state because we have no transition that comments on that. No transition originates from the stop state that goes somewhere else when we brake. So we're going to go ahead and add in these missing transitions essentially. So we know what happens on the stop state when we hit the gas, but what happens when we hit the brake? Well, if we hit the brake when we're stopped, we are going to stay in the stop state. So we're going to make a transition from the stop state back to itself when we brake, and we're going to do a similar thing over here on the moving state. We don't know what happens when we hit the gas on the moving state, so let's add in this transition. So when we hit the gas on the moving state, we're going to stay in the moving state. So we now have a transition for each possible action on each state. And this is going to become very important later when we talk about DFAs, because this is sort of like a necessary condition for something to be considered a DFA. But this is really all we need to go ahead and move forward. We know that we have some states that we can be in and a way to transition between these states. So now that I've introduced a very basic example of a finite state machine, I want to go ahead and introduce an actual DFA. And I'm not going to formally define it yet. I'm going to more so show you guys a DFA and kind of explain the purpose of a DFA. And that's going to hopefully segue us very easily into the formal definition. So let me go ahead and draw a very simple example of a DFA here. And there is going to be some new notation here, but don't worry about it. I'll make sure to explain everything. So let's see, we want a self loop on 1. Let's make an except state over here, label this Q2, make a self loop on 1, and loop back on 0. Okay, so this is an example of a DFA. Now, You may notice a lot of similarities between the DFA and the finite state machine, and that's because, well, a DFA is a finite state machine. It's just a specific example of one. So we still have states. We have our state labeled Q1 and our state labeled Q2, and we have transitions between those states represented by the arrows. Now, you may notice we're using particular characters. We're using zeros and ones, and there's a few more extra things here, like we have this arrow pointing into Q1 from nothing over here, and we have a double circle around Q2. This is all stuff that specifically applies to DFAs and things like that. So I'll go ahead and introduce that notation after I explain what a DFA actually does. So what does a DFA do? Well, it essentially reads in strings of characters, and depending on the string and the transitions that are taken based on the characters, it either accepts or rejects the string. And that might be all cool and fine, but you may be asking, what exactly is the point of that? Like, what is this modeling? Well, the thing that a DFA is modeling is actually a computer. This is an abstract representation of what a computer is doing, essentially. It's not the most powerful one that we can make, but it is a basic one that helps us understand certain problems. So why is this sort of a representation of a computer? Well, all a computer is doing fundamentally is manipulating strings of characters that are either 0 or 1. So this actually models a computer very well. It actually helps model certain algorithms. So for example, you can create DFAs that accept strings of a certain pattern and reject all other strings that do not fit the pattern. So it kind of helps you determine whether or not a problem is computable by a computer. So that's kind of the whole point of these abstract models of machines, is that they help us determine which problems are solvable and unsolvable on computers and which problems are solvable efficiently or not. So a DFA processes strings of characters, and depending on the string, it is either going to accept or reject the string. And this is an abstract model of what a computer is doing at the most basic level. So I think the best way to sort of understand what's going on here is to do this by example. So let's say we have a string s, and let's have it be equal to 1, 0, 1, 0. So we want to go ahead and process the string on our DFA and determine whether the DFA accepts or rejects the string. So in order to do that, I need to introduce this extra notation here. So what exactly is this arrow here? Well, this arrow indicates that Q1 is the start state of the DFA. So anytime you've got an arrow pointing from seemingly nothing to a state in the DFA, that indicates that that state is the start state. So I'll write it over here so we don't forget that. Q1 is the start state of the DFA. Okay, so that's that piece of notation, and the only other thing that we don't really recognize here is this double circle. So what does this represent? Well, this means that Q2 is an accept state. So if you ever see a double circle state, then that state is an accept state. And all states that don't have a double circle are not accept states. So let's write it over here. Q2 is an accept state. Okay, so these are our new pieces of notation. And we're going to go ahead and see how we process strings based on everything that we have here. So when we're processing strings on a DFA, we want to process them character by character. So we first want to process the character 1. Now, what do we do here? Well, this arrow indicates that Q1 is the start state. So we are going to process our first character on the start state. So essentially, we're going to start on Q1, and we want to take the transition that corresponds to our first character, which happens to be 1. So that's this transition right here. So we're going to take the transition corresponding to the character 1, and we're going to end up back at Q1. So we've just moved from Q1 to Q1 by reading the character 1. Okay, so let's repeat the process again. So we're currently on Q1 after making that transition, and we want to process this next character. So we're on Q1, and we want to take the transition corresponding to the character 0, which is this transition. So we're going to transition from Q1 to Q2 on the character 0. Okay, so we've transitioned to Q2. Now we want to process the next character on the state Q2, because that's where we currently are. So the transition corresponding to the character 1 on Q2 is this one right here. So we're going to transition from Q2 back to Q2. And finally, we want to process this last 0 on Q2. And the transition corresponding to 0 is this one. So that's going to take us from Q2 to Q1. Okay, so we've processed all of the characters in our string, and now we need to determine whether the string was accepted or rejected. So in order to do that, we need to only look at the last state that we ended on and determine whether it's an accept state or not an accept state. So notice that we ended on Q1 and it doesn't have a double circle around it. So we know that we ended on a not accept state. So that means that we are going to reject the string. However, if we process a string and we ended processing the string on Q2, because Q2 is an accept state, we would accept that string. But in this case, because we ended on Q1 after processing all characters, we are going to reject the string. So the string 0101 is rejected by the DFA. Okay, so we've just seen an example of what a DFA does and how to determine whether a string is accepted or rejected by a particular DFA. And now that we sort of understand all of the new notation and sort of what a DFA is doing, I think we can get into the formal definition now. So I'll go ahead and erase all of this. And I'm going to leave our old DFA up here for reference when we're doing the formal definition. So I'm going to go ahead and write this in again. We've got our start state Q1. We transition to Q1 on the character 1. We transition to Q2 on the character 0. Q2 is an accept state, so we're going to use a double circle. We transition back to Q2 on character 1 and to Q1 on character 0. So this is the DFA that we just looked at. Okay, so we're going to formally define exactly what a DFA is, and this is very important because this allows us to determine what a DFA is and is not. So if you see an example of some sort of finite state machine that doesn't follow all the conditions of a DFA, then you can determine whether or not it is a DFA, which is why this is important. So a DFA consists of 5 different things. And the first condition is that it must contain a finite set of states Q. So we're calling the set of states Q. That's what this Q is. So a DFA must have a finite set of states Q. So let's go ahead and look at our example of a DFA over here. Is this condition satisfied? Well, our states are Q1 and Q2, and that is a finite number of states. So we indeed have a finite number of states, which is the set Q1, Q2. Okay, so this condition is satisfied by our example DFA. So we haven't violated anything yet. So condition 2 is that we must have a finite alphabet sigma. Now, what is an alphabet? Well, the alphabet is all of the potential characters that our DFA can process. So if we look to our DFA here, the alphabet must be the set containing the characters 0 and 1, because our string can't read off any other characters other than 0 or 1. So in other words, if we say wanted to read in the character A on this DFA, we wouldn't be able to do that because there are no transitions for the character A. So our finite alphabet for this example DFA is the set containing 0 and 1. So again, the alphabet, just to reiterate, is the set of all of the possible characters that can be in your strings. So it's the set of the characters that the DFA can read, essentially. So we do indeed have a finite alphabet for our example DFA, so this condition is satisfied. Okay, condition 3 is going to be the hardest. It's going to contain some higher level math notation, but I just want you to stick with me. I'm going to try to make it as simple as possible. So condition 3 is that we must have a transition function, and we're going to call it delta. And then this is going to be some fancier math notation, but I'll make sure to explain it really well. So we have a function delta that maps elements from Q cross sigma to Q. Okay, so this may look complicated, but it's really not. So I'm going to explain what's going on here. So this first part before the arrow is the domain of the function, and this second part over here is the codomain. So let me just label this to make it more clear. This is the domain of the function. This is the codomain. Okay, so we are mapping elements from the domain Q cross sigma to the codomain Q. Now, what the heck is Q cross sigma? Well, this X here means the Cartesian product, and all the Cartesian product of two sets is all of the possible ordered pairs from each set. So an example of something in Q cross sigma from our example DFA over here would be the ordered pair Q1, 0. I drew that really bad, hold on. Q1, 0. This is in the set Q cross sigma. And you'll notice the first element of the ordered pair is a state, and the second element of the ordered pair is a character from the alphabet. So Q cross sigma is simply all of the ordered pairs consisting of this states from the set of states and characters from the alphabet. So that's all Q cross sigma is. So basically, we are mapping state character pairs to another state, and that's representing these transition arrows up here. So if we wanted to represent this one transition on Q1 up here, like in a mathematical sense, we would write that delta of Q1 1 equals Q1. So as you can see, we're just mapping a state character pair to a state. We're saying that when the character 1 is read in on the state Q1, we transition to Q1. That's what this is representing. So this delta transition function here is just simply representing all of our transitions. And so we need to get into a few more details here before we move on, though, because there's a few details that matter here. So because delta is a function, every state character pair must have a defined state that it maps to. We can't have a state character pair that does not map to anything by the definition of a function. Everything in the domain must have a mapping to something in the codomain. So essentially what that means for our DFA is that for every state, every character must have a transition on that state. So you'll notice here we have a transition on Q1 for the characters 1 and 0, and the same holds for Q2. We have a transition for the character 1 and the character 0. So to make this a lot clearer, if I were to erase this 0 transition here, let's say, this is no longer a valid DFA because we don't have a transition for the character 0 on the state Q2. So we need to have a transition for the character 0 for this to be valid. So the important thing here is that every state must have a transition for every character. Okay, so now that we've covered that, the other detail that we need to consider is basically the fact that a mapping from the domain may not have two outputs in the codomain, essentially. So a state character pair cannot map to more than one state. So what that means for our DFA is we can't have two transitions for the character 1. We can't have, say, this transition here from Q1 to Q2 on the character 1, because now the ordered pair Q1, 1 maps to Q2 and Q1. So this is no longer a function by definition. We have more than one output per input. So that is not allowed. And let me go ahead and redraw this. This eraser is kind of annoying. So we transition on 0 and transition on 0. Okay. So the two details to keep in mind is that we must have a transition for each character on each state, and we may only map to one character, or we may only map to one state per character. So that was really the hardest part of the whole definition. So if we made it through that, we can make it through the last two. So number 4, the fourth condition is that the DFA must have a start state. So we must have a start state, and we'll label it Q0 in the set of states. So every DFA must have one and only one start state. So this essentially implies that a DFA must at least have one state, essentially. So every DFA must have one and only one start state to be considered valid. So up here in our example, This arrow indicates that Q1 is a start state, and we have no other start states, so that condition is satisfied by this DFA. Now, our last condition of a DFA is that we must have a set of accept states, and we'll label it F, which is a subset of the set of states. So essentially all this means is that we either have 0 or more accept states in our DFA. So, and that's because the empty set is a subset of every other set. It's not really that important, but we can basically have 0 accept states, or we can have some of our states be accept states, or all of our states can be accept states. So any number of accept states that you draw into a DFA is going to satisfy condition 5. We can have any amount of accept states, so long as those accept states are states defined in the set of states Q. So let's make sure that this condition is satisfied by our example. We have one accept state, which is Q2. So F is equal to the set containing Q2, and Q2 is indeed a subset of Q. So we have a valid set of accept states. Now, this is all a DFA is. It just has to meet these 5 conditions, and it is a valid DFA. So I'm going to go ahead and do one more example of a DFA just to put this into practice so that we can determine whether a DFA is valid or not. And outside of this video, I would also encourage you to go ahead and draw some example DFAs and determine whether they're valid based on this definition. But I'll go ahead and go through one other practice problem here. So let's say we have 3 states in this DFA. I'll label them Q1, Q2, and Q3. Let's say we have our start state be Q1, and let's define the alphabet to be, here, let me separate this really quick. There we go. Let's say our alphabet is just the characters 0 and 1. And a quick side note, on pretty much every DFA problem, the alphabet is always going to be 0, 1. And again, this is because computers fundamentally only read strings of that consist of the characters 0 and 1. So you're really only going to see this alphabet in most cases when dealing with computer science theory questions. So we have a finite alphabet sigma. We've got a finite set of states Q. That's all good. We've got exactly one start state. So those 3 conditions are satisfied. We do have a set of accept states F, which is none of them, but let's make it a little more interesting and make Q3 an accept state. Perfect. So Q3 is our accept state. We have a valid set of accept states. Now all we need to do is make a well-defined transition function. So we just need to add in all of the transitions here. Now, remember, every state must have a transition for every character. So on Q1, we need a transition for both the character 0 and 1, and that needs to happen for every one of our states. So on Q1, let's say we transition to Q2 on 0 and back to itself on 1. Let's say on Q2 that we move to Q1 on 1 and to Q3 on 0. And on Q3, let's say we loop back to itself on both 0 and 1. Now, is this a valid DFA? Well, we already know that all these other 4 conditions are satisfied. We have a finite set of states, a finite alphabet, one and only one start state, and a set of accept states, such that the set is a subset of Q. However, for our transition function, we need to make sure that it's well defined. So on Q1, we have a transition for both 1 and 0, so that's okay. On Q2, we have a transition for both 1 and 0, and we have the same thing for Q3. So we indeed have a well-defined transition function, and thus all of these conditions are met. So this construction over here is a valid DFA. Now, if I were to take out the 0 transition here, we would suddenly not have a valid DFA because we don't have a transition for every character on Q2 anymore. So the transition function is no longer well defined. So that was an example of creating a valid DFA. And I would encourage you outside of this video to go ahead and try a few examples on your own, create some states and some transitions, and make sure that the transition function is well defined and make sure that all of the conditions hold. And if you can get that to happen, then you have built yourself a valid DFA. In the next video that I make on computer science theory, I'm going to talk about regular languages, which tie heavily into DFAs, and then I'll do a bunch of practice problems on constructing DFAs that recognize regular languages. So that's about it. See you guys later.